Welcome to the next session, my dear students. In the previous session, we have discussed about the alkalinity, hardness, kind of chemical impurities, and we are continuing the chemical impurities further. So we are going to discuss what are the different kinds of metallic ions and what are the different kinds of non-metallic ions and what are the different kinds of dissolved gases, and in metals also what are the toxic metals, non-toxic metals that are present in water and what are their limits and all we are going to discuss in this session. Okay, so apart from multivalent metallic cations causing hardness and negatively charged anions causing the alkalinity, there are some other chemical compounds also. Let us discuss one by one. So here next one is chlorides. Chlorides as a Cl minus. So chlorine is a disinfectant but not chloride. So chloride Cl minus, whenever there is a charge then it is unstable. Whenever any compound which is unstable present in water is harmful to human beings. So that is why chlorides are not good for health if it exceeds the limit of 250 mg per liter. It should not be more than 250 mg per liter. Okay, chlorides should not be more than 250 mg per liter, and in no alternative source, if no alternative source is present, then under unavoidable conditions it can be relaxed up to 1000 mg per liter. It can be relaxed up to 1000 mg per liter. This is for chlorides. See here, we will discuss what is the test we use to determine the chloride content, and what is the titrant, and what is the indicator, and what is the color change, and what will be the effect if it is more than this specified limits. These things we will learn in each and every impurity. Okay, so it is estimated using Morse method. It is estimated using Morse method, and the titrant here is silver nitrate. Titrant is silver nitrate, that is AgNO3. Silver nitrate is a titrant, and the indicator is potassium chromate. Indicator is potassium chromate. Potassium chromate is the indicator, and the color change is yellow to brick red. Yellow to brick red. This is the color change. Okay, this is the color change. And if it is more than the specified limit, it causes kidney ailments. If it present in excess, it causes cardiac problems It causes these are the effects of exceeded chloride doses in water. Okay, so this is all about chlorides. So all these limits are as per IS 10500 2012 only. And next one is sulfates. Sulfates as SO4. sulfates as SO4. Sulfates as SO4, its limit is, it should not be more than 200 mg per liter and it should not be more than 400 mg per liter. I told that for total alkalinity, small correction, for total alkalinity, the limit should not be more than 200 under ideal conditions and it should not be more than 600 under unavoidable circumstances. It is relaxed up to 600. I was told 400. I have told the sulfate limit here for total alkalinity. So please make a note. So for total alkalinity, the upper limit, the relaxation was given up to 600 mg per liter. Okay. So 600 mg per liter is the revised limit, and for sulfate it is 400. 200 is the lower limit, that is it should not be more than 200 mg per liter under ideal conditions when no alternative source is available. In that case we can relax it up to 400 mg per liter, but it should not be more than that. Okay, so here it is estimated using turbidimetry technique. Turbidimetry technique using barium. So turbidimetry technique means how we determine the turbidity. So like light scattering, light absorption techniques and all. So those techniques we will use to determine sulfates, because sulfate will be present in the form of a precipitate. So precipitate is nothing but a suspended matter or settled matter. So this settled matter can be kept under suspension and we can determine what is the concentration of that suspended matter using turbidimetry techniques. So that is why how we determine the sulfates. Okay, we determine the sulfates. Here if it is present in excess, it causes laxative effect. Laxative effect, that is nothing but diarrhea, nothing but loose motions. So if it is present in excess then specified, then it causes diarrhea or nothing but laxative problems. Okay, so next is dissolved oxygen. Dissolved oxygen. See, the dissolved oxygen is very, very important for human survival, because all the impurities we want less or we don't want at all, but this oxygen we want. This is not an impurity, so this is what is required in water, because when oxygen is present, all the impurities will get oxidized by the oxygen and it gives a freshness to the water. By oxidizing all the organic matter or by oxidizing all the metallic ions. So by dissolving completely the gases, so all these things will get removed when it is present, that oxygen is present. So oxygen is needed in water, so in the form of dissolved form. So dissolved oxygen. So this dissolved oxygen is determined using Winkler's method. So it is determined using Winkler's method. Here in Winkler's method, what we do is there are two stages in this test. In the first stage, we will find whether the dissolved oxygen is present or not. So in the first stage, what we do is in the first stage we add manganese sulfate, MnSO4, manganese sulfate plus alkali iodide azide. We add manganese sulfate, alkali iodide azide to water, to raw water. Okay. So if brown precipitate is formed, it indicates the presence of DO. If no precipitate or white precipitate, colorless, is formed, it indicates absence of DO. So if brown precipitate is formed, that means so the DO is present. When no precipitate is formed means DO is absent. That is very, very important bit they ask. So when you add this manganese sulfate and alkali iodide azide, so brown or white precipitate will form. That means this DO is present or absent. Now we understood. Now what we do is again, so whatever be the brown precipitate, this brown precipitate is nothing but the dissolved oxygen. So you have made the dissolved oxygen into a form of a precipitate. Now in order to estimate the dissolved oxygen concentration, you need to again mix this precipitate into the water. For doing it, so before doing the titration, we need to again mix this brown precipitate into the water. In order to make it, we will add H2SO4. So what we do is we add H2SO4 to this brown precipitate, again to get DO dissolved. Okay, whatever the DO now formed in the form of a precipitate will get dissolved when you add H2SO4 to that brown precipitate, and it forms a yellow solution. Okay, and forms yellow solution. So that yellow solution is nothing but the dissolved, again the oxygen is dissolved into the water. So yellow solution will form. So now using this yellow solution we will do the titration. Okay. So now what is the titrant? So this is only to find whether the dissolved oxygen is present or not. This is the first stage. In second stage we do titration. So titrant. So in second stage we perform titration. So titrant is sodium thiosulfate. Sodium thiosulfate. Thiosulfate is the titrant. Sodium thiosulfate is the titrant, and the indicator is starch. Indicator is starch. So here So we use this technique to find the DO, okay, to find the DO. Next is fluorine. So this is all about the dissolved oxygen. So everything is important. Method name is important. So the reagents which we use to determine the presence of oxygen, that means the manganese sulfate and alkali iodide azide. So what are the reagents? They may ask like this: what are the reagents we use to determine the DO presence? So we use manganese sulfate and alkali iodide azide. So which form of precipitate will which type of precipitate will form when DO is present? So that is brown precipitate, or else if brown precipitate is formed when we add the reagents, then it indicates the presence of DO, the absence of DO, like that many questions can be formed. And what is the titrant which we use in Winkler's method? The titrant is sodium thiosulfate. And what is the indicator we use to determine the dissolved oxygen? That is starch. So all these things are very, very important for the GATE examination 1 mark questions. Okay, every point which I have written on the board is a one question, one mark question. Otherwise I don't write it. Now next is fluorides. See, fluoride is a chemical impurity. It's a special kind of chemical impurity because if it is less, also it is harmful. If it is more, also it is harmful. So there is a specified limit. Why fluoride is important for examination is, whichever the impurity, whatever be the impurity we discuss, we always say it should not be maximum, it should not be more than this, it should be always kept inside this limit. But fluorine is not like that. It should be kept in a specified limits. If it is less, also it is harmful. If it is more, also it is harmful. So the limits specified for fluoride is 1 to 1.5 mg per liter. 1 to 1.5 mg per liter. Okay, so this is the limit of fluorine as fluorides. Okay, if it is less than 1 mg per liter, then what happens? If it is less than 1 mg per liter, then it causes dental cavities. It causes dental cavities. Fluorine deficiency causes dental cavities. See, whenever you are facing some kind of problem with the root of the teeth, then doctor will give you some kind of paste which is having fluorine and potassium kind of paste. They will suggest you to use because it enhances the strength of the cavity, dental cavity. Okay, so when the fluorine is present, it will react with enamel, that is the coating on the teeth. So whatever with the white coating on the teeth, so that is nothing but enamel. So this fluorine will react with that enamel and strengthens the enamel. Okay, the fluorine will react with the enamel and it strengthens the enamel, which gives the teeth a good finishing texture. Okay, otherwise what happens when this deficiency comes? So you will observe a kind of yellow patches on the teeth. So that is dental cavities. In that form also we can say that is dental cavity when the enamel is not having fluorine in it. So it will form kind of yellow patches on the top. Okay, if fluorides is more than 1.5, so now the fluorine not only react with enamel, it also reacts with the calcium which is present inside the teeth. Okay, so calcium present inside the teeth then causes mottling of teeth. mottling of teeth. So if it is reacting more, then it causes mottling. Mottling means what I told you now. So it forms yellow patches on the teeth. Okay, it forms yellow patches on teeth. Yellow patches on the teeth, as well as we call that bone fluorosis. We call a disease called fluorosis, dental fluorosis and skeletal or bone fluorosis. Okay, so fluorosis means it's a disease because of the reaction of the fluorine, because of the reaction of fluorine with calcium. So how the bone is getting the strength? It is cemented by calcium. Even the teeth, bones, all are strong compounds. The strength is coming from the cementing nature of calcium. So if the calcium is not present, that calcium is being used by fluorine, because calcium is a cation, fluoride is an anion, strong anion, it is a strong cation. So the fluorine and calcium are having greater affinity towards each other. So because of which the calcium will leave the bones and react with the fluorine and becomes a precipitate. And even in the teeth also, whatever the calcium present will go out of your teeth and react with the fluorine present in the water. So it causes fluorosis. We can call it as dental fluorosis. If it is happening in teeth, we call it as dental fluorosis. And if it is happening in bones, skeleton, we call it as skeletal fluorosis or simply bone fluorosis. So when the calcium present in the bones or the teeth, if it is getting reacted with the fluorine, when it is more than 1.5, so generally less than 2.5, this dental fluorosis will happen. Only the damage is confined to teeth when the concentrations are approximately 1.5 to 2.25 like that. If it is more than 2.5, then it also spreads to the skeleton of the body. So if it is very high, the concentration of fluorine, then it also spreads to the human body and it damages the human body also. Okay, greater than 5 mg per liter causes skeletal fluorosis, and if it is approximately 1.5 to 2.5 like that, so it causes the dental fluorosis. Okay, so that is why generally we need to keep the fluorine within these limits only. So in this topic we only confine ourselves to the limits. Okay, and what happens if it exceeds the limit, that thing only we will confine in this topic. So how to bring the water which is having less fluorine or more fluorine into the specified limits, that we will discuss in the treatment part. So we will discuss all those things in the treatment part. Okay, so this is about fluorides. And next is, and it is estimated using colorimetry technique. It is estimated colorimetry methods using zirconium. Okay, using zirconium. So this is all about fluorides. So next is nitrates or nitrogen compounds. Nitrate, so all those things, ammonia, nitrogen compounds. Why this nitrogen compound is very important is because if you go to the sewage treatment, then we will understand why this nitrogen compound is very important. Because see, whatever be the sewage you take, any biodegradable matter may contain two kinds of compounds. One is carbon compounds, another one is nitrogen compounds. In our treatment units, so in our treatment plants, we generally take care of carbonaceous demand or carbon demand. Whatever the demand of oxygen that is arising because of the carbon, that we will take care in the treatment units. Whereas whatever be the nitrogenous demand, nitrogen's demand, that we allow it to happen in the nature, because when nitrogenous demand is allowed in nature, it will enhance the nutrient value of the soil. So to enhance the nutrient value of the soil, we allow this nitrogen compounds to get stabilized on their own in the nature, because it is not harmful to the nature, but it is harmful to human when it exceeds to some limit. So that is why these nitrogen compounds are necessary for the plant growth and all, but not needed for humans. So that is why we need to put some kind of interest in understanding the nitrogen compounds. So what are the different kinds of nitrogen compounds? Nitrogen compounds. So nitrogen compounds. So generally nitrogen compound, what is the byproduct of the nitrogen compound during the organic activity? The nitrogen compound which comes out is in the form of ammonia. So it comes in the form of ammonia. So the first stage of nitrogen compound is ammonia nitrogen. Ammonia nitrogen. And next format is, so this ammonia nitrogen starts, it becomes an organic matter, and that nitrogen is called organic nitrogen. Organic nitrogen. So this organic nitrogen is ready to decompose. It is about to decompose. This is what is ammonia, is a fresh waste, fresh sewage entered into the source, and now it has to create a favorable conditions to start decomposing. So once the favorable conditions are being attained, then it will form into organic nitrogen, so which indicates that it is ready to start decay, ready to decompose. So third one is nitrates. So during its stage of decomposition, this organic nitrogen, it becomes nitrate. Nitrate means it needs some kind of oxygen. It is in its path of decomposition. It is in its path to attain the stability. So this is a highly unstable location where it needs lot of oxygen. Where it needs lot of oxygen, demand will be more. If the oxygen demand is not sufficiently available, it will pull whatever the oxygen present in its vicinity. If this is present in the water, then it will pull the oxygen. It will just take the oxygen from your body also. So that much active it is. It is having a lot of affinity towards oxygen. Because it is unstable. Nitrite is unstable. And once it got all the sufficient oxygen needed to it decomposition, then it will become nitrate. So this is a stable form of nitrogen compound. So the ammonia nitrogen indicates a recent pollution, fresh sewage. It indicates recent pollution. So whatever the pollutant which is coming out of the treatment units, so where in treatment unit we will take care of carbonaceous demand, but we don't take care of nitrogenous demand in treatment unit. That nitrogen compound will come into the source again, or else it will come onto the land again, or else it will come onto the sea again. So wherever you are dumping it, so there this pollution will enter. But as far as water supply is concerned, we only see that the pollutant when entered into the moving stream from where we take the water for our water supply. So it indicates the recent pollution in a moving stream. Okay, now so after some time, so it creates a favorable condition for its decomposition at that stage. So that is called organic nitrogen. When organic nitrogen formed indicates that is old pollution and ready for decomposition. It is old pollution. It is old pollution which is ready for decomposition. It is ready for decomposition. So this nitrogen is also called as albuminoid nitrogen. So this nitrogen is called albuminoid. Albuminoid nitrogen. Albuminoid nitrogen. Okay, so it indicates the pollution which is ready for decomposition. Nitrite, it indicates active decomposition. It indicates, this is indicates intermediate stage of decomposition. Intermediate stage of decomposition where oxygen demand is very high. Where oxygen demand is very high. Okay, so this is the last stage of decomposition, stable. This is a stable format of nitrogen. So this is nothing but a stable form of nitrogen compound. Fully oxidized form. Fully oxidized form. Okay, so these are the nitrogen compounds. These are the nitrogen compounds present, and we call this as Kjeldahl nitrogen. So we call this as summing of 1 and 2. 1 plus 2 is called total Kjeldahl. Total Kjeldahl nitrogen. Total Kjeldahl nitrogen, or we simply call it as TKN. Simply we call it as TKN, total Kjeldahl nitrogen. Ammonia nitrogen plus organic nitrogen, or ammonia nitrogen plus albuminoid nitrogen is called total Kjeldahl nitrogen. Total Kjeldahl nitrogen will give us an understanding about how much nitrogen is present for decomposition. How much nitrogen is present for decomposition, that we will understand from total Kjeldahl nitrogen. That is the importance of total Kjeldahl nitrogen. Okay, so here the IS code has given limits for each and every kind of nitrogenous compound. Let us see what are the limits given. So for ammonia nitrogen, the limit is 0.15 mg per liter. Should not be more than 0.15 mg per liter. Okay, for organic nitrogen, it is should not be more than 0.3. Should not be more than 0.3 mg per liter. And nitrites, very important, it is highly unstable. That is why, so the limit is nil. No, we don't at all need 0. So it is 0. So we don't need any nitrite to be present in drinking water. Nitrate, it is a stable form, that is why it should not be more than 45 ppm. It should not be more than 45 ppm. Okay, so likewise, if you see, organic nitrogen is just fresh sewage, fresh compound, so that is why generally the limit is very less. Whereas if you look at the nitrate, it is completely stabilized. It is completely stabilized. That is why it was given a higher limit. And there is no relaxations are being given to the nitrogen compounds. So these are the limits. If the limit is increased, for example, if the limit of nitrate increases more than 45 ppm, it causes methamoglobemia. Okay, methamoglobemia. If nitrates greater than 45 ppm, then it causes methamoglobemia. So in this methamoglobemia, the hemoglobin in blood will react with the nitrates. Okay, it reacts with the nitrates and forms methamoglobemia, because of which the body color changes into blue. And this disease is predominant in infants. That is why we call this disease as blue baby disease. It is called blue baby disease. So when this disease comes, the infant or babies will turn into blue color because of this hemoglobin is being reacted with the nitrate and forms methamoglobemia. So because of which the color of the body changes to blue. Okay, so that is why generally we have to keep this limit in less than 45 ppm. Okay, so these are all non-metallic impurities present in the water. So there are some kind of metallic impurities are also present. So again, in metals, we have classified the metals as toxic metals and non-toxic metals. Non-toxic metals are needed for the body growth, whereas toxic metals are not at all needed. So let us see what are the non-toxic metals, what are the toxic metals and all. Let us see. Okay. See, metals, non-toxic. Non-toxic metals such as calcium, potassium, sodium, iron, manganese and zinc. So these are all different kinds of non-toxic metals. Toxic metals such as arsenic, barium, cadmium, chromium, lead, mercury, cyanide, etc. So these are the toxic. There are many. These are the important toxic metals which are not at all needed. See here, the limits and all, we can refer IS 10500. So the limits, so all the toxic metals limits are not needed, as well as all the non-toxic metal limits are also not needed. So whatever is important for the examinations, those limits I will specify. So rest of the limits are not needed. If you want the limits of all, so you can refer the IS 10500 2012 for the limits, for the latest limits. If you want to learn all the limits of toxic, all the limits of non-toxic metals, you can refer the code IS 10500. In that everything was given. Okay, so if you in this, the important non-toxic which we discuss is iron and manganese. Iron and manganese, why it is important? Because iron and manganese, it causes color. Wherever it present, it causes color. Okay, so iron oxide, if you look at the construction industry, like if you are using cement, if you are using a brick, so if you are going to soil mechanics, if you are seeing a laterite soil, so everywhere you go, wherever iron is present, it is causing some kind of color to the compound where it is present, right? So it is having a behavior of imparting color. Similarly, if iron and manganese are present in water, iron, manganese, so manganese, if present in water, it imparts color to the clothes. If you are using this water for washing of clothes, it imparts color. It imparts color to the clothes washed using this water. So that is why it is not needed. It is not needed. That is why it is not needed. How much it is required for the human being, that we will take, and rest is not needed for, because it causes color problems to the clothes and all. So that is why iron, the limit of iron as per IS 10500 2012 is 0.3 mg per liter. It should not be more than 0.3 mg per liter. Similarly, manganese should not be more than 0.1 mg per liter. Manganese should not be more than 0.1 mg per liter. So these are the limits given by the Indian Standard Code. Okay, there is no relaxation was given. So these are the latest limits. 0.1 is the latest limit. You need to, earlier the limit was 0.05, but now the limit is 0.1 mg per liter, and it is also estimated using colorimetry technique. So it is estimated using colorimetric procedure. Okay, so this is about iron and manganese. So these are all the important metallic ions needs to be discussed. There are some kind of toxic metals limits I told you already. You can refer the IS code. So these are the important chemical characteristics of the water. These are the important chemical characteristics of the water. So what we will do is, we will discuss the biological characteristics in the next session. Thank you so much.